Hi, I'm going to be presenting Bypassing Windows Defender. Defender is the default antivirus solution built into Microsoft Windows. I go by Char, and you can reach me on Mastodon at char@knock.social. You can also reach me on the DC719 and SBWasp Discord servers. I also actively support the SBWasp Meetup, which you can find on meetup.com. In addition, I have a set of GitLab repositories on gitlab.com/hack_char. You will be able to find a copy of these slides on that GitLab page. This is my standard disclaimer. When attempting to develop something to bypass antivirus, you're going to be triggering that antivirus. On a work computer, you are definitely going to be triggering endpoint detection and response. Do not do this without written approval. You will make your company's security team very sad, which will then make you very sad as you look for a new job. Ideally, developing something like this should be done either on a separate, isolated computer or within virtual machines. While you are not likely to be infecting yourself accidentally, it is quite good to segregate this type of work from everything else. Microsoft Defender, the consumer-grade antivirus, is considered a top product by AV-Test. As you can see here, it compares quite favorably to other antivirus software. This is not to be confused with Defender for Endpoint, which is an EDR product. EDR solutions are intended to flag any malicious activity for security teams to follow up on. On the other hand, antivirus products are designed to err on the side of usability and not generate false positives. If you are relying only on antivirus to prevent running malicious code, you are going to be very, very sorry. The following presentation will demonstrate a very well-known approach to bypassing Defender and likely many other antivirus software products as well. Everyone's primary solution to avoiding malware should be to not introduce that malware in the first place. If you're going to be browsing social media, clicking on links in random emails, downloading and executing anything, do that on a separate computer that you accept might get infected. That is not to say you should disable antivirus or not use it. You should be using it, and please, 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 if you see an alert, take it very seriously. If you do not have a separate computer, you're best off at least using a different virtual machine. If that also doesn't work for you, at the very least, please use a separate user and password. User-to-user isolation on modern patched operating systems is actually pretty good, and at the very least is going to prevent that malware immediately getting access to all of your data. For this presentation, I will be using meterpreter as my payload. It is ubiquitous and well known as a malicious to pretty much every antivirus and EDR product. It's also open source, easy to get. There's plenty of documentation on how to use it. This payload will execute on Windows 11 and provide remote access from a malicious host. You can find it in the Metasploit framework. I am using a virtual machine lab. In this lab environment, I have a Windows 11 virtual machine that is fully patched and running as a normal user, that is, not elevated to an administrator. The other virtual machine is running Kali Linux. They both have internet access. This demonstration at the end will show running a few commands on Windows 11 to transfer the initial payload from our attacking host over port 80 or HTTP. This will execute without showing any warnings, errors, or alerts of any kind, and open a channel back to the Kali Linux host, allowing someone on that host to control the Windows 11 host. The Windows 11 virtual machine is fully patched. For reference, the last update was September 2023 cumulative update. Also, all of the Defender options are fully enabled and no exceptions are entered. I even enabled automatic sample submission, although if you're developing something that is malicious, you probably don't want to be enabling that. As you will see later, it, however, doesn't likely make that much of a difference. On the attacking host, it is running Kali Linux. I will be using the Metasploit framework throughout this presentation. Specifically, I will use the Metasploit console to listen for a callback from the Windows virtual machine. The Windows virtual machine will be executing the meterpreter payload. That meterpreter payload will be generated using MSF Venom. I will also be using a simple Python web server to host the initial malicious code. Let's start by generating a basic meterpreter payload executable file. Windows Defender will be using signature and heuristic detection and should detect this payload very easily. It is important, though, to see what it does. That is, what does a user see when this happens? Opening a PowerShell console and copying the payload to the user's folder does not trigger antivirus. However, opening the folder in Explorer immediately causes the payload to be quarantined. That is, it removes it from the folder and shows a very scary warning. The details show pretty accurately that it has found Metasploit. That is, really meterpreter, a payload in Metasploit, but pretty accurate nonetheless. Let's try some basic XOR encoding. The -E or encoding flag is added and another executable generated with MSF Venom. Transferring it over to Windows and opening Explorer again detects the payload and quarantines it yet again. For the heck of it, let's try adding the -I flag and causing this to be XORed 1,000 times. Perhaps not surprisingly, it's still detected and quarantined. If you look at the XOR encoder, all it does is statically XOR the payload with the ANSI capital A character. For what it's worth, doing that any even number of times will just produce the original payload. Although it does increase the size each time, so there's at least a chance there's a header being added. In any case, doesn't really matter, it's detected. So let's try the Zato-Dekiru payload, which is a much better approach. It's still an XOR obfuscation, but at least it uses a randomly generated string each time to XOR with. Also, it uses some tricky floating point unit assembly code to help obfuscate a little bit better. However, generating this executable with MSF Venom and transferring it over still triggers the alert and quarantines the file. What is needed is something called a loader. That is the general approach to bypass any antivirus, and for that matter, EDR even. It's going to place our malicious code into memory and execute it for us. Ideally, it will do this without Defender even seeing it. But at the very least, we need to bypass the signature and heuristic detections. I'm going to use a small custom loader to help bypass signature detection. I will also use some basic obfuscation, such as that Zato-Dekiru, as well as encoding each stage and delaying the loading of Meterpreter's API. While this will bypass Defender, it's highly likely to be detected and perhaps even automatically blocked by EDR. This basic approach I am demonstrating is widely documented and available online from many different blogs and papers. First, I'll generate the malicious shellcode. Using MSF Venom, I am generating a C# formatted meterpreter payload that is Zato-Dekiru encoded. You'll see it spits out a nice bit of text that I can simply copy and paste into the C# based loader. Also, I'm using the staged version of the meterpreter payload. That means the initial code is very small and needs to grab more code from a remote host before finally doing its thing. While this minimizes the initial code and potential for signatures, it does behave like malicious code in that it grabs something remote and executes it. Sometimes that behavior is more likely to be detected than just putting all of the payload into the malicious code. To turn this malicious set of bytes into executed code, please refer to this blog post from 2021. Most of the loader is straight from it, although it does have a few modifications that I made. Loaders essentially do the same thing. They put code into memory and execute it. As antivirus and EDR evolves to detect it, malware developers just change things up a little bit. They can use a different language or procedural steps and can often break whatever signature-based detection is in place. It may even change the behavior enough to bypass a behavioral detection. This example is using C#. That is a programming language considered memory safe. That is, the programmer does not manage the memory. However, we do want to manually muck about with the memory. That is easily accomplished by using something called pinvoke or platform invoke. This is a well-documented thing on Microsoft MSDN and an official approach to call a function that is not otherwise available to C# code. You'll see that the resulting binary file only shows mscore DLL as an import. It does not show any of the DLLs you're actually grabbing a function from. It does, though, leave a static indication of the function name and its signature in the instruction address table. So it should not be difficult for AV or EDR to see the pinvoke method is used and what functions are being called. This technique for loading malware is at least 6 or 7 years old. However, it still does work. In short, we're turning these bytes into MSF Venom generated executable code on the target Windows 11 virtual machine. To make sure we don't trigger a heuristic detection, I'm only loading executable code in my own process. That is, I'm not trying to muck about with a different process. I am also not attempting to modify the system in any way, such as trying to bypass AMSI. AMSI, AMSI, is the anti-malware scanning interface. Way back a few years ago, antivirus would do all kinds of things like hooking system calls and messing around with the kernel. It made the OS unstable in many cases. Microsoft decided there has to be a standard way for all antivirus to work, and so there came about AMSI. There's plenty of bypasses for AMSI and EDR. There's plenty of bypasses for AMSI, and EDR still hooks functions and messes around with the OS, as it's the only way to reliably detect malicious activity. The approach being shown will load in stages. That reduces the initial surface area that might be detected via signatures. It also encodes in order to help avoid signatures. A delay is added in loading the final API, and that also helps obfuscate what we're doing. Here's the first half of the loader. It's just defining a new class and the pinvoke functions that we'll be using. You can find the correct pinvoke syntax either straight from Microsoft MSDN, pinvoke.net, or at least one or more GitHub repos, and likely many other places. The actual function is the last half of this code. I did not include the full byte buffer generated from MSF Venom here, since it's just copy-pasted anyway. First, a new memory page is allocated, read and write. Then, some memory is allocated in that page and marked as execute, read, and write. That right there should really be detected, and at least an EDR would likely report that, if not actually prevent it. The byte array is then copied into that memory area, a thread is created, and last but not least, it waits for that thread. It's important to wait for the thread, otherwise, given the way we're running this, the process would die and immediately kill the thread. This simple code is going to be compiled into a DLL using Visual Studio 2019. I like to use that in .NET 4 as it's better backwards compatible. The first time around when I compiled this, I had automatic submission enabled, and a pop-up asked if I wouldn't mind submitting it to Microsoft to see if it's quote unquote safe. So for the hell of it, I let it. Nothing happened, that is, no alerts. Also, this only happened when the DLL was compiled and written to disk. However, fast forward one day later and the AV signatures get updated. The DLL that I generated and used the day before now got detected and quarantined. Not sure why it was marked as whack attack or whatever that is. It's likely that this process required some human to do some cursory review and click yes, this is a malicious thing button. So even if it does get sent to Microsoft, there would be likely a significant delay and you'd have plenty of time to execute the code without warnings or errors. In any case, I just reran MSF Venom, which generated a new set of shellcode where Zutudikiru made a new random XOR key. Copying that into the source code, compiling it, and generating a new DLL did not get detected or alerted on. Again, I'm going to show using Visual Studio 2019 to generate this DLL. It's likely this resulting DLL is also Windows 10 compatible, but if it's an old enough version, the pinvoke signatures are likely to be wrong and have at least a chance of causing it not to work. I have read, however, that even if they are off a little tiny bit, it should still work. First, create a new project. In the filter, pick C#, Windows, and Library. Then choose the Class Library.NET framework. I have not tested out the other types of libraries. Choose .NET 4 and then create. Go ahead and enter the code. Choose release instead of debug. That should strip out any symbols and help obfuscate the DLL just a little bit better. Choose build. If you feel like it, let Defender get a sample. I would avoid that if you're trying to use it much later though. Transfer this malicious DLL over to your Kali virtual machine. A simple Python web server is then being used to distribute this DLL to our targeted Windows 11 box. Also, open up MSF console and start using exploit multi-handler. The options shown here were used. Note that it's important to choose enable stage encoding true and auto load standard API false. This does help obfuscate the connection just a little bit better. Now to transfer the payload and trigger it on the Windows 11 target. Let's go ahead and use PowerShell as it's a very common approach. Ideally, it should avoid logging. Even better, it should run straight from memory and avoid any submissions sent back to Microsoft. By default, no advanced PowerShell logging, such as script block logging or module logging, is enabled. However, any of these suspicious commands will still show up in a Windows PowerShell event log. During my testing, I saw it as an event ID 800, although it may show up in others as well. I have not found an authoritative list of these suspicious commands for Microsoft. This was taken from a presentation by Kerry Roberts on exploring PowerShell logging with Telltale. In any case, I'm not going to use any of these functions. Here's the 5 PowerShell commands needed to get the malicious DLL into a variable first without writing it to disk. It then coerces it into an assembly code. Then choose the namespace, class, and function. Finally, run it. Note that it will hang the console at this point. Here's the actual values pasted into the Windows 11 virtual machine. No need to base64 encode or otherwise obscure them. Back on Kali in the MSF console, there is a new session opened. No errors or warnings show up on the Windows 11 host. Control of the Windows 11 host from the Kali virtual machine is now possible as the user that ran those PowerShell commands. For the heck of it, I checked which process I was in. It's clear it's just running as the PowerShell terminal. And now for a short demo showing these steps in real time. This is a short demo showing how to get meterpreter to run on a fully patched Windows 11 VM. First, I'm going to show you that this is a truly fully patched VM. So here we just finished running update. Next, I'm going to go over here to security. And we'll even go ahead and turn on fully, including sample submission. So those are all on. Next, we're going to go over to our Kali VM. And first, we're going to go ahead and make sure that we've got the malicious DLL here. And I'm going to go ahead and host it off of port 80 on a basic web server. Over here, we're going to go ahead and run MSF console. And here under the console, we're going to go ahead and set up exploit multi-handler. Oops. And run that off of port 8080. Back to our VM, we're going to go ahead and run a basic terminal, which defaults to PowerShell now in Windows 11. And I'm going to go ahead and copy and paste these 4 PowerShell commands. You notice it does not return from this. Back over here, we see meterpreter is opened a session. Oops. Got to remember to do this load standard API since that wasn't loaded automatically, specifically to avoid detection. And it's interesting that it shows Windows 10, but that's just because for whatever reason Microsoft decided to call it a Windows 11 major version still 10. If I go to shell here, call out system info, you'll see it is Windows 11 Pro, the same VM that I'm on. And we can run a shell, do whatever we want, totally bypass Defender. And last but not least, a few references for your reading pleasure. If you'd like a copy of these slides, they will be at gitlab.com/hack_char. Thanks for watching.